In the kinetic theory of gases, which gives us a theoretical basis for PV equals nRT and a lot of other properties that we've been using, including the properties, the specific heats, the constant volume, constant pressure, specific heats for diatomic and monatomic gases, and so forth. We have these models. Okay, the first model of the kinetic theory is a simplistic model consisting of one molecule moving in just one direction in, let's say, some cylinder, bouncing back and forth here without any change in speed. The speed is given by v. The velocity is directed parallel to an axis of this cylinder, and the molecule is colliding perfectly elastically with the ends of the cylinders, the ends of the cylinder. Okay? We want to find the pressure on one end of the cylinder. We assume a cross-sectional area A so that the area of the end of the cylinder is A. In order to find the pressure here, we're going to find the force exerted, the average force exerted by this molecule on this end. Now that average force we're going to get from the impulse momentum theorem. The average force is the average rate at which momentum changes at this end. And that's equal then to the total change of momentum over a time interval divided by the length of the time interval. So the change of momentum for a single collision at this end is m delta v, mass times change of velocity. The mass isn't changing, so the only thing that can change the momentum is the velocity. That's why we get m delta v. And that equals 2mv. Now, why do we say that's 2mv? Well, the velocity comes in, and it's in this direction. It leaves, and it's in this direction. So, for example, the velocity could come in at positive 10 meters per second and leave at negative 10 meters per second. If it comes in at 10 meters per second and stops, that's a change of velocity of negative 10 meters per second. If it then, from rest, goes to negative 10 meters per second, that's another negative 10 meters per second. So the velocity would change by a total of 20 meters per second. It doesn't change by just mv, it changes by 2mv in this elastic collision. We're of course assuming that the mass of the molecule is much less than the mass of the cylinder, so that the cylinder doesn't carry away any of the kinetic energy or any of the momentum. It'll carry some momentum, but it won't carry any of the kinetic energy. Okay, so massive cylinder, so that all the kinetic energy remains in the molecule. Okay, the delta T between the collisions. Okay, we got our delta P, we've got to divide by a delta T. And for delta T, we're going to use the time between collisions. We could use any delta T we wanted to. We could use an hour if we wanted to, but we're just going to use the convenient delta T that's the total time between collisions with an end of the cylinder. Now that delta T is going to be whatever distance the object travels between collisions divided by its velocity. How far does the molecule travel between collisions with this end of the cylinder? It travels twice the length of the cylinder itself. Now, there's a little confusion here often. Why do we say it travels twice the length when it makes another collision in here? We're not interested in collisions with this end. We're trying to measure the pressure on this end. If we want the pressure on this end, we'll worry about collisions with this end, but not this end. So we're just interested in collisions with this end of the cylinder. So we're going to say that those collisions happen every time the molecule makes a round trip, which is of course the case. Okay, in that case our delta T is going to be twice the length divided by the velocity. From this it follows that the average force exerted on an end of the cylinder is just delta P divided by delta T. And let's zoom in on this a little bit so we can see it clearly. And that's going to be 2mv divided by your 2L over V. If we simplify this, we're going to get mv squared over L. When we see mv squared, what do we think of? That looks a lot like kinetic energy, except kinetic energy has a 1/2 in front of it. So mv squared is double the kinetic energy, double the 1/2 mv squared of kinetic energy. So we see that the average force exerted here could be expressed as twice the kinetic energy of the molecule divided by the length of the container. The average pressure exerted is therefore average force over area, and that's going to be, using this form, mv squared over area times L. Now area times length is volume. Now notice I'm using a big V for volume and a little v for velocity. Okay? And of course, since mv squared is twice kinetic energy, we could say the average pressure is twice the kinetic energy of the molecule divided by the velocity. Now we've defined temperature as something that is directly proportional to the kinetic energy, the average kinetic energy of the molecules in a substance. And we're being a little bit circular here. But if we get too rigorous, it's going to be too hard to follow. So I'm going to just quote this result and say that what we mean by temperature is something that's proportional to kinetic energy. And so kinetic energy, of course, is proportional to temperature. Whatever this constant is, then, the average pressure will be that constant times the temperature over V. Now you see that we're approaching PV equals nRT. If we put the V over here, we get PV, and we got T over here. If this constant is somehow equal to nR, then we're going to have our ideal gas law. Now, in this example, the molecule was moving strictly in one direction along the axis of the cylinder, and there was just one molecule. Next, we'll look at what happens if we have more than one molecule, and if the molecules are moving in random directions in three-dimensional space.